Okay, just 1 second, because okay, very good. So good afternoon, and I sent a message because I make the shift in the calendar of the lectures. So I will teach next Wednesday and not the Wednesday, April 12. Are you attending next Wednesday in presence? Yeah, very good, perfect. This is perfectly fine. Okay, so let's move forward. This is our usual reference web page. Today we talk about drawings, and in particular the design of drawings. We already talked about drawings, and today we go into the details of their design. So it's a lecture that is organized as usual with the PowerPoint at the end. So I take it and I open the PowerPoint for delivering the lecture. Here it is. Let me pass to the presentation mode. Very good. So here we start with a picture of some drawings. Drawings are structures that aim to mitigate coastal erosion, and to give to beaches the desired shape. They are used, drawings, in the presence of beaches, which are, on the one hand, they are very prone to erosion because beaches are formed by sand, as we know, by definition of beach. And on the other hand, they are usually very important. They play a key role for recreation, for tourism. They have a relevant socioeconomic value, as we know. And therefore, they are, on the one hand, prone to erosion. On the other hand, they need protection. You already know how beaches can be protected because Professor Archetti taught the design of breakwaters. And last time, in my last lecture, I gave some information, some qualitative information on the interventions that we can use to limit coastal erosion. And of course, I mentioned also groins. What you can see here, it's a picture of groins. First of all, they have a particular shape. They are Y-shaped groins. Usually in their most elementary structure, they are just walls that protrude into the sea along a direction that is more or less perpendicular to the coastline. We will see that it's not precisely perpendicular, but in many cases, they are indeed oriented perpendicularly to the dominant direction of the coastline. And in their, as I said, elementary shape, they are just like the teeth of a comb, of a comb with very large gaps. And in this case, they have this particular shape because they tried to strengthen their action against erosion, their protection against erosion. And in this case, you see that they are formed by boulders, by putting boulders in place, like breakwaters, yes. And this is the solution that is most typically used. In this solution, according to this solution, they are not very permeable to sediment transport. In some cases, we want this kind of intervention, these groins, to play a more moderate role, to play a more smooth role in mitigating erosion, and therefore we may use permeable groins with windows in a way. We will see the details later. This is, let me anticipate, and we will discuss it later. Groins mitigate the sediment transport in the along shore direction. They are not very effective in the across shore direction. They also play a minor role to mitigate cross-shore sediment transport because they, in a way, mitigate the strength, mitigate the energy of the wave motion. And also they originate diffraction. They, in a way, tend to smooth the energy of waves also in the cross-shore direction. So, I mean, there is indeed also an action in the on the cross-shore sediment transport, but their main purpose is to mitigate the along-shore sediment transport, which is something that usually is acting, evolves along a long time scale, while across shore sediment transport, most of it is originated by storms. Most of the along-shore sediment transport is originated by smooth waves, by currents, and therefore it evolves along according to a longer time scale. This is important to be considered because breakwater are more intended to contrast seasonal sediment transport, while groins are intended to mitigate the longshore sediment transport over all seasons. So for this reason, when there are both components, we may see groins that are coupled with breakwaters, even if you understand that groins from the point of view of the visual appearance of the beach, they look like bracks. Even when you walk along the beach, you see here, you cannot walk along the beach by keeping your feet into the shallow water. At a certain point, you have to bypass the groin. So in terms of visual appearance of the beach, they are, even groins are a little bit impacting. And the breakwaters, on the other hand, they are impacting because you can't see the skyline, you can't see the full width of the sea. So if you put all of them in place, it looks like the beach becomes a sequence of pools. And also the circulation of water, it's important to keep the quality of the beach. So when you couple both solutions, you have to be careful. Now, so let's provide a definition. We define groins as a shore perpendicular, as I said, structure, which aims at maintaining the beach behind them and controlling the amount of sand moving along shore. Controlling means that we don't want to fully stop the sand. It's important that sand continues to circulate. So for this reason, I mentioned permeability. Keep in mind that this is a natural process which is originated by the imbalance that is caused by the sediment transport of rivers. So rivers bring fine sediments typically when we are in locations where beaches originated naturally. It means that these locations typically are characterized by a flat land behind the coast, and being flat is characterized also by the inflow into the ocean of rivers with very reduced slope. If a river has a reduced slope, it means that the energy of the flow, of the river flow, is low. Because, the river takes energy, the river flow takes energy from the slope, from gravity, which means the slope of the bed. So in this case, rivers are characterized by a flow with low energy, which means that the sediments transported by the river are very fine, are very small. And the reason is that the coarser sediments, the bigger boulders, already sedimented upstream when the energy of the river flow decreased. So this river brings a lot of fine sediments at the river mouth. It may be a delta or maybe an estuary. And these fine sediments, once that they get into the sea, they settle down. They settle down because at the coastline, there is a confrontation between the energy of the river flow and the energy of waves. So they, in a way, balance each other. and the sediments settle down. So there is an accumulation of sediments in correspondence of the river mouth. And these sediments, of course, create an imbalance, because if you travel along the coastline, you get into a region where there are a lot of sediments, and therefore the reaction of the system is to bring these sediments along the coast, distribute them. For very obvious reasoning related to energy balance. To give you an idea of the amount of sediments that a river may deliver, we may refer to the Po River. And the Po River was diverted in the year 1476, I think, by the Venice Republic, which at that time was very flourishing, and they were much concerned by the rapid advance of the Po River, of the land, into the Mediterranean Sea. And they were concerned that they could get locked. And so they diverted the Po River south. So the current delta of the Po River, if you look at it, is shifted towards the south, because about 500 years ago, almost 600 years ago, the Republic of Venice diverted it. And to give you another piece of information, at present, we estimate that the advance of the Po River into the Adriatic Sea, it's about 14 meters per year. And then this advance is contrasted by the coastal erosion. But if we didn't have any coastal erosion, the advance would be about 14 meters per year. And still, if you look at the maps of 100 years ago of the Po River Delta, you see that you can notice a significant advance, which has been reduced around 1970, 1980, 1990 for the removal of sediments from the Po River. Why? Because they needed sediments to make the concrete and to pave the roads. So in 1960, 1970, when they built in Italy the highways, they took a lot of sediments from the Po River, and this decreased the sediment delivery. But today, the sediment delivery is more or less undisturbed. Another reason why the sediment delivery may be mitigated is the presence of river barrages. But in the Po River, there are no barrages. There is only one in close to Piacenza, but it's not keeping a notable volume of sediments upstream. But where they built river barrages, they indeed experienced a decrease of the delivery of sediment. So as a whole, the system is, let's say, into equilibrium. By definition, nature is never in equilibrium, but because it's evolving, it's continuously evolving towards new states. But in the time scale of the human civilization, we can say that in this relatively short time scale, the system is in equilibrium. It's in equilibrium with sediment delivery brought by the rivers and sediment transport along coast. And then there can be some interventions by humans who alter the equilibrium, and coastal erosion may be amplified in some locations. And therefore, we need to make intervention like groins in order to, in a way, re-establish the equilibrium. So you can see here, it is stressed once again that groins mitigate the volume of a longshore sediment transport. Okay, before I move forward, I go back to the first slide. You see the spelling, I already mentioned this to you. It's can be with a Y or with a I. And it depends on the US or American English. I don't remember which one is US and which one is UK, sorry. US and American are synonyms. Which one is US and which one is UK? Okay, so here you see some examples of coastal erosion where an intervention with groins may help. So on the right, you see that the coastal erosion is threatening some houses, and it's characterized the situation by an intrusion of water into the land. The same thing on the right, on a scale that is less concerning, but still you see that for the increased erosion, they had to manage some protections. Keep in mind that in this case, I'm not really sure whether the coastal erosion was caused by a cross-shore rather than a long-shore sediment transport. But the shape of the beach on the left does suggest to me the idea that it's something that is very extended, and the shape of the beach suggests that this is something that is probably originated with a good contribution of the long-shore sediment transport. On the right, it's difficult to say something. Okay, now let's give some more details. First of all, groins can be small structures, or they may be very long. We distinguish between long and short groins depending on how far across the surf zone they extend. Remember, the surf zone is the zone that is comprised between the coastline and the average position of wave breaking. So this is called the surf zone, which is characterized by a very energetic environment. And usually groins, to give you an order of magnitude, are extended beyond the closure of the surf zone. So these groins that traverse the entire surf zone are considered long. But we may have situations where we don't want to really stop all the longshore sediment transport, and therefore we may adopt short groins, which don't cross along the whole surf zone, but stop earlier than that, closer to the coastline than that. Okay, you know, these are relative terms. Of course, we know that the extension of the surf zone varies with wave height, of course. Let's say that we refer to provide this definition to the average, as I said, position of wave breaking. On the other hand, we don't need a strict classification, just to give you an idea that you may distinguish the groins. They can be short or they can be longer. And of course, we also know that in some season, groins, for instance, in the summer season, they may act as long groins, and in the winter season as short groins. What happens, in order to clarify the idea, what happens to sediment transport when groins are in place? It is stopped, but when it accumulates, behind a certain volume of accumulated sediments, it's clear that the forcing becomes more effective in removing them and moving them behind the groin. So what happens, it may be that the level of the sand increases, so in a way drowning part of the groin, burying part of the groin under the sand. And in this case, when there is high tide, we may have sand bypassing the groin over it. In other cases, we may have a sand bypass beyond the head of the groin. The head of the groin is the end of the groin seaward. It may be also called groin tip or groin toe, T-O-E. Usually it's called head, but also in some cases you may see the term tip. Groins can also be classified as either high or low, depending on how high their crest, The crest is the top of the groin where you can walk usually. How high is the crest relative to prevailing beach level, beach berm? Conventionally, we take the level of the berm. High groins have crest elevation above the normal high tide level and above the limit of wave run-up on the beach. So it's problematic for the sand to bypass them by passing over. Why? You understand, if their crest is lower than the high tide level, it's possible for the sand to bypass. Okay, so short and long groins, low and high groins. Now, of course, I already mentioned that they have a limited effectiveness to mitigate the across-shore sediment transport. Okay, this is fine. And they also may be inefficient if there is a high tidal range, large high. You understand why? And so it is more typical to find groins where the excursion of the tide is limited. If you think of the Atlantic coast in the north of France, you typically don't find groins there. There is a tide excursion that is so high, think at Mont Saint-Michel, that you can drive by car over it when the tide is low, and it's completely divided. It's an island when the tide is high. So in these conditions, it's the use of groins, it's useless. Bypassing over the groin is often called overpassing. Bypassing actually, it's meant to indicate the bypass of sand beyond the head of the groin. Overpassing is the bypassing of sand over the groin. And we know that terms are important. Okay, where then groins are more effective when a longshore sediment transport is dominant, and also when the coastline is changing in curvature, because if you have changes in the direction of the coastline and sharp changes, these places are more prone to erosion. So if you think, for instance, at a concave shape, just let me use the blackboard a little bit. So if you have a coastline with a concavity, and here there is the land, and here there is the sea, and you have a circulation across shore sediments along this direction, you understand that you probably find a beach here. Okay, so you probably find here a beach. There is deposition. It's quite typical when you have a small bays into cliff coasts to find beaches there. Conversely, if you have a shape with a convexity, it's likely that you have erosion here. It's also for reasons of equilibrium, you know. For reasons of equilibrium, naturally, the equilibrium configuration tends to minimize the singularities along the coastline to smooth it. There is a reason why the coastline of the Adriatic Sea, which is made almost continuously by beaches, is completely straight, because the singularities have been smoothed out. So other situations where groins are expected to be more effective, it's a situation where an intruding sand is to be managed, such in correspondence of river deltas or estuaries, at the downdrift side of a large harbor breakwater, and other situations where a longshore sediment transport is a reason of concern. Downdrift means the direction. Just one second. Let's suppose that we have a coastline here. And let's suppose that here we have a breakwater. And let's suppose that the dominant wave direction is this one. So downdrift means this side of the breakwater. And this side of the breakwater, keep in mind that what are we expecting here? We are expecting that the beach is protected by the breakwater, is protected against the across-shore sediment transport. So what we are expecting is an accretion of the beach in correspondence of the breakwater. But then, for reasons of equilibrium, downdrift the breakwater, which means downdrift on the other side of the breakwater with respect to the dominant wave direction, we may expect here a concentration of erosion. Because it's the longshore sediment transport is a little bit mitigated by the breakwater here, and therefore downstream you have the same action by waves, but you don't have sediment delivery from the zone that is protected by the breakwater. And therefore here you may expect downdrift, you may expect this problem, and for this reason sometimes it may be appropriate to put a groin here. And in this case, let's put in this like here. In this case, probably the groin, for the reasons that we will see later, may be more appropriate to displace it tilted in this direction. We will explain later why. Okay, now permeability, which I already introduced. Groins may be not permeable or permeable to sediments. Typically, groin made by boulders are impermeable unless you structure them in a way to allow some windows in the body. But usually when we use boulders, this is not the case. And when we use boulders, as we will see the typical structure of a groin, we assume that it's not permeable. So when do we use impermeable groins that are not permeable? When we want to be very effective in blocking a longshore sediment transport at most. This, as I said, may turn out to be a too strong action. And therefore, if we want to mitigate, if we want to keep some sediment transport, and there are many situations which indeed, where indeed it could be more appropriate to keep part of it, then permeable groins are precisely designed so that an appreciable quantity, a significant quantity of the available littoral drift, so available sediment transport, will pass directly through its structural component. These groins are typically built with wood elements. There are several figures that we can find on the web of woody groins. Woody groins. Let's see if I can find something immediately. Not yet. So, okay, you see some examples here. This is, if you look at this one, this is not really a groin, it's a coastal protection because it's a sea defense. They are called groins, but actually I wouldn't define them as groins according to our definition because they are displaced along the coastline direction. But still, it's very interesting what they did here. You see that it's permeable. It doesn't completely stop the waves, and because they don't completely stop the waves, they are less exposed to the forcing of waves, so they are more resilient. On the other hand, they clearly significantly decrease the energy of waves. So this may be indeed an effective coastal protection. Here you see an example of woody structures. These are groins indeed, and you see they are very permeable because they are simply made by very small piles that are put into the sand, but still they are effective. This one is another interesting example. You have this kind of very, very low protection, continuous protection that is very low, and then the head of the crest of the groin is continuously interrupted with windows. Still, they are effective. And you can see also the effectiveness here. It's nice, this figure, because you see that the waves on the downdrift side of the groin, the downdrift side is this one, where there is my mouse. The waves are, the run-up of waves is less significant. Other example, it's this one. This is still a groin, and you see it's wood in the first part, and then
sorry, Marco.
Yeah. Yeah, it's not
green.
It's not.
You're not sharing.
Sorry, Giorgio.
Don't worry, no problem.
I didn't realize that you were here, but still, I should have. Just 1 second. I should have shared the screen anyway. 1 second, because for some reason I don't understand. It's not working. Let me see. I think. Let me go here. No, it's not here. I don't understand why. Let me see. One second, Georgia. I'm trying to share and okay, now it works. Good. Now you should see it. I hope so. Yeah, you can see it. Okay, so as I said, there are boulders here to protect the groin in the vicinity in the proximity of the sea. Here there is another example, and let's see. This is another example. You see that the structure can be really different. There is a lot of diversity. It also depends on the material that is available, and it depends also on the context, because of course we try in most of the cases to give a look at this structure as natural as possible. So for instance, you see here, this is, okay, this is also an artistic picture, but it's another example of a structure that indeed looks natural. And they wanted here to make a protection that it's clearly artificial, but it's the appearance, it's environmentally friendly. Okay, and this is another example which I think is significant, and this is given by the Wikipedia page. By the way, it is linked in my web pages, and in the Wikipedia page there are several nice pictures of drawings. This is a nice, another nice example. You see that the appearance is not so bad. Of course, here the picture is taken like an artistic picture, but here is another example along a river. I think this is these are river drawings. They are frequently used along rivers, again, to mitigate the river bank erosion. And this is again a river. And here, what is interesting is to look at the effect. You see that between the groins, the beach takes a moon shape. It's moon-shaped, and you can clearly recognize what is here downdrift and where is updrift. So updrift is towards the bottom of the picture, and updrift is towards downstream, in this case, is towards the high part of the picture. And you recognize this because if you look at the coastline on the right, at the beginning, there is vegetation, and vegetation clearly indicates more stability. And you see that the coastline, the river bank, is more advanced with respect to the downstream part. There is a big difference. There is a big difference because, of course, by blocking the sediments in the downstream part, you have to expect a kind of increased erosion. And therefore, which is due to the fact that there is no accretion, and therefore, given that you capture the sediment delivery upstream, there is no accretion downstream. And so the shape that is taken by the beaches is, as I said, like the shape of the moon. And of course, you understand that the gap between the groin is needs to be carefully designed, as well as the orientation of the groin. So you understand that in this case, if the groin is perpendicular, you get a particular shape. If the groin is oriented downdrift, the shape changes. And the opposite if the groin is oriented updrift. This is another example of a woody groin. This is, I would say, again, woody. And you see here, this one looks like a short groin. It's not extended up to the surf zone. This is a groin, a boulder groin. Again, river groins. Here you can see once again the difference in the position of the coastline, etc. This is a coastal groin coupled with revetments, I would say. And this is a groin that is made by a concrete structure, but it's permeable. You see that it's permeable. Again, these are boulder groins. Here there are other examples of groins. I think only one here, which is more, I think it's more a pierre than a groin. But probably, I'm not really sure if these are where my mouse is placed, if this one is the result of an artificial intervention. But you can see clearly here what is the effect the effect of this shape of the coastline. Actually, here it's not easy to find an interpretation, because I would say that here probably downdrift is here. There is more erosion, there is accretion here, and downdrift looks like here. But it's not easy to find an interpretation. If you look at the waves now, they don't help. Anyway. Okay, so now let's go into the details of the design, because these are structures that are not easy to design, because we need to elaborate an interpretation of the functioning of a system which is characterized by a very relevant randomness into the future. And when you are in such a condition of uncertainty, the ideal situation is the possibility to include some flexibility in the design, some possibility to adjust the shape of the groin later on. And it might be the case also that if we have time, usually we don't have time. When you have to design interventions, we don't have a long time usually. It may be also useful to move forward with steps. Like if I have to protect a long piece of beach, it would be useful to protect a first piece, look what happens after a couple of years, and then move forward. If we don't have time, it is very useful to look at the current situation of the beach. If we can find other groins built in the past, in the proximity of the beach, it is a very relevant information to look at what happened after the groin construction in a similar context. Even if it's not close, we may look for contexts that are similar, maybe far away in space, but similar, in order to get an information, to get an idea of how it may work. So in a way, the first thing that we need to know is wave behaviors, like for any coastal intervention. And the wave behaviors, of course, are the leading parameters of the longshore sediment transport, and therefore we need a statistical analysis of wave forcing, dominant wave direction, and also if we have data of sediment transport in some locations they are available, we need to make an assessment of sediment forcing, which is strictly related to wave forcing. Also, keep in mind that if you look at other experiences, you realize that it's very unlikely that when you build a groin, you accrete, you extend the beach up to the head of the groin. Usually, the sediment accumulation reaches an equilibrium at some distance between some distance from the head of the groin. So we need to understand, this is our basic rule for design, under the assumption that we protrude a groin into the sea up to a certain distance, we need an understanding of how much the beach will itself protrude, accrete, gain space into the sea. So this is the basic parameter that we need to use. And of course, the effectiveness of the intervention, the beach accretion, will depend on some leading parameters. One leading parameter is the length, the extension of the groin, of course. If the groin is short, we can expect a small accretion. If the groin is longer, it's a longer accretion. But there are also other leading parameters like the gap, the spacing. Another leading parameter is the orientation of the groin and the shape of the head, because the groin may be rectilinear or T-shaped. Of course, you understand that a T-shaped groin is like a combination between a groin and a breakwater, and we expect it to be more effective. So now we try to understand how we can decipher the structure, the shape of the beach after the groin realization, after the groin construction. So let's look at some experiences, as I said. Here I put a note which is related to another relevant question. The relevant question is whether or not we should make the groin permeable or not. It depends on the level of blockage that we want to reach, but it also depends on the time that we are given for beach accretion for the groin to be effective. In some of the cases, we observed, and this is the first bullet point here, that the filling of the groin compartments is very slow. And even after, you see this example, 3 decades, they found that the beach was still progressing, and therefore the intervention was still far from reaching equilibrium. I wanted to put it here because I think it's a relevant indication. So the relevant indication is that in some cases, the time required to reach equilibrium may be long, and therefore also the timing is a parameter that needs to be evaluated. So permeability, yes, it's fine, but we have to expect that if a groin is permeable, I mean, the higher the permeability, the longer the time scale that is required to reach the full effectiveness of the intervention. So here there is a bullet point list of the parameters that determine the response of the shoreline to groins. And these parameters can be divided into 3 groups. The first group is the parameters related to groin structure. So we already mentioned length, we already mentioned spacing, we already mentioned elevation, high or low groin, we already mentioned the porosity, and also we already mentioned, let me forget for now tapering, the angle to the shoreline, and we already mentioned the shape. Let's forget for now tapering, and we will discuss it later. So now let's better inspect what are the dominant feature, depending on the context, and how we can quantify the effect of each of these parameters. There are parameters related to beach and sediments, the second category. So the depth at tip of groin, tip is a synonym, as I said, for head. The beach morphology, slope of the beach, height of the berm, presence or absence of the dune, shape of the shoreline, which we already discussed, the depth at the average breaker line or beach closure, sediment availability, grain size and variability of grain size, sediment density, which is another important parameter. The third category is the parameters related to waves, wind and tide. And these are wave height and variability, wave period and variability, the usual parameters that we know, wave direction and variability, and wind speed, wind direction, wind duration, and also the tidal range. Okay, now let's try to get quantitative. I anticipate that we will start with an empirical approach. It's a kind of rule of thumb which is anyway giving a very useful indication. And then this empirical approach can be used for preliminary design in order to get a preliminary idea, or for making the preliminary design that in some cases is required also to get the authorization for developing the final and executive design. And then I anticipate that in order to give a detailed prediction of the evolution of the beach, we use usually numerical models. But you know, numerical models also entail the requirement of a lot of information. So in any case, let's start with the empirical rule. And the empirical rule, which is very important, is very relevant. As I said, it's carried out by following what is called the lambda shoreline rule, or lambda 1/3 rule. It is relatively recent, and we will see a picture here. I anticipate before moving to the picture. Oh, okay, let's start with the picture first. So, what is the lambda rule? The lambda rule says that if you have two groins, like in this case, forget about the T-shape on the right. For now, let's assume that the right groin is rectilinear and not T-shaped. If you indicate with G the gap between the groins, the low water shoreline, after reaching the equilibrium, will be placed, and you see here the low water shoreline indicated with the acronym LWS, will be placed at a distance from the head of the groin that is equal to lambda G. G is the gap, where lambda typically takes the value 1/3. So this is the rule of thumb. This is the answer to the question. So the question was, where can I expect to find the new shoreline, the low water shoreline? The reply is, take the gap of the groin, 1/3 of the gap of the groin, and measure the distance between the groin head and the new low water shoreline. This is very simple. Actually, what you see here in dashed line, the blue dashed line in correspondence of the left groin, is what will actually happen. So we don't get a fully rectilinear shoreline after reaching equilibrium, as we see if we look at the blue continuous large blue line. But we get something like the blue dashed line. So an accumulation of the sand updrift and an increased erosion downdrift. An increased erosion with respect to the new low water shoreline. Of course, we don't have an increased erosion with respect to the old situation. And you can assume that the pre-project coastline is the position of the berm after, before the project is given by the black line. And here it's also indicated the high water shoreline, which is placed at a distance W from the low water shoreline. We will discuss it later. Of course, the distance W depends on the tidal range, okay? And we can indicate with capital S the gain in beach that we got with the groins. Now, let's consider the T-shaped groin. You see how the distance lambda G is measured. It's measured from the extreme hand of the groin. So what is the effect of the T? Is to cause clearly, also it looks obvious, an accumulation of sand updrift with respect to the situation without the T. There is more accumulation because the sand gets trapped there. So the low water shoreline will reach a position that is more shifted seaward, and the final end of the new beach, of the new low water shoreline, along the body of the groin will be placed at the distance lambda g from the extremity of the T, from the seaward extremity of the T. And what we have to expect downdrift is an increased erosion. Now, let's go back a couple of slides to describe what we just said in words, better describe in formal words. Okay, so the rule, the lambda shoreline rule, or lambda 1/3 rule, says that the post-project coastline during the mean low water level is located between about lambda 1/3 and lambda 2/3 of the distance between adjacent groins measured behind the structure's seaward face. So here you see an additional information. Lambda, I said, is 1/3, but this is an optimistic prediction because in energetic environments, it could increase up to 2/3. In fact, you see the last bullet points here, last bullet point. Larger lambda values that may even exceed 2/3 may be appropriate for energetic environments. Larger distances between groins. Why larger distances? Because clearly this is an empirical rule. It works for an ideal distance. We will see what is the ideal distance. I anticipate on average 20 meters. But if you space the groins more, you get closer to an undisturbed situation in between, and therefore, it is to be expected they are more effective. Okay, and in particular if the environment is very energetic, and also if you have uncertainty in the whole design process, it's clear that uncertainty may lead to both damage and opportunity. I mean, if there is uncertainty in a design, it may happen that you underestimate the forcing, but you may also overestimate it. And therefore, in principle, uncertainty shouldn't induce a bias towards a higher risk. But actually, what it turns out is that in the presence of uncertainty, what often happens is that the result is not as good as we expected. It happens very rarely that the result is better than what we expected. Why? Because in the presence of uncertainty, we have a bias. It is very unlikely that the bias implies that we are more conservative. Usually the bias, for several reasons, implies that we tend to be less conservative, because in the presence of uncertainty, we tend to be optimistic. We tend to adopt the solution leading to the minimum concern. Because it is, I think it is part of our instinct, of our natural attitude. In the presence of uncertainty, we try to be optimistic, because this is the way to survive. When you are in a difficult situation, the way to survive is to be optimistic. But actually, this means that very often, in the presence of uncertainty, we have to expect that the solutions are less effective with respect to what we as preliminarily estimated. And therefore, here, this is the reason why uncertainty means that you may get a larger lambda value. So uncertainty indeed means, from the point of view of the engineer, that you should increase your safety factor. So in the presence of uncertainty, let's reduce the gap between the groin, maybe, and let's try to, if it's possible, to extend them into the sea a little bit more. Okay, second slide. It's already, I already anticipated this consideration. Larger lambda values imply a more prudent design. And these values for lambda, of course, are confirmed by several field observations. Usually empirical rules are derived based on the experience. The experience may be done into the lab, but in this case, the lambda rule has been confirmed by many experiences. One more detail that I didn't anticipate so far, the rule is considered applicable where the angle between the wave crest and the line connecting the tips of the structures, let's call it control line, is small. That is lower than 25-30 degrees. So wave crest, it's better if it's nearly parallel to the control line. So let's be clear. And I anticipated this, with this figure here, this consideration, this suggestion. So let's get a beach where Giorgio, you can't see the blackboard, but now I am, just 1 second. I am trying to, okay, now I think, yeah, not so easy for you to see it. And I put it into evidence. Okay. Okay. Okay, so we have this coastline, and we have this wave direction, which means that this is the wave crest. And let me make the coastline, because it's already, here it's parallel to the wave crest, so it's not a good example. Suppose that the coastline is this one, so the groins should be oriented in this direction. This is to increase their effectiveness in trapping the sediments. Of course, this is the general indication. Maximizing the effectiveness of the groins means that you get the most of accretion updrift, but you also get most of the erosion downdrift. So the new coastline here will be something like this. Sorry. This will be the new coastline. Of course, as I said, there is some tolerance. You may tolerate an angle between the wave crest and the direction of the groins and the control line, sorry, of about here the control line will be this one. This is the control line. So you can get an angle, you can tolerate an angle of about 25-30 degrees. And if you want, for some reason, to minimize the erosion downstream, you may, in a way, change the orientation, increase this angle. Because it's clear that if you increase the angle between the wave crest and the control line, you decrease the efficiency of the groin, you decrease the accumulation of sediment updrift, and you decrease also the erosion downdrift. So in some cases, you may want, if you want to smooth out the effect of the groins, to change to increase the angle. Okay, now. We already discussed this figure here. Then, this is another example. This is another example where you see that the orientation of the T is shaped in a way to make the control line almost parallel to the wave crest. You see gap is approximately aligned with the dominant wave crest. And you see the application of the lambda rule in this case. Okay, I already mentioned this consideration. Actually, what we get is not precisely the shape that is suggested by the lambda rule, but it's a smooth version. And also here, the local context, the local features become extremely important, and it becomes important also the seasonality of the wave forcing. And if we want to better inspect in detail what the configuration will likely be, we need a more refined modeling, as I said, a numerical modeling, which we will discuss also, at the end of this lecture today. Now, there are also other empirical rules that can be coupled with the lambda rule, which we don't discuss here. We don't discuss here. These empirical rules basically also try to take into account the diffraction and the diffraction of the wave forcing, which is induced by the presence of the groin. So the empirical part of it is not limited, is not confined to the lambda rule only, but as I said, I prefer not to discuss the other rules here, because the lambda rule is what really is providing the most important suggestion. Now, if we want to estimate, if we want to design the groins, there are 12 steps which are suggested by a reference. I think it's the USDA manual, or the US ACE manual. I think the full reference is given in my website, and I think it's also available. These steps are summarized here in a qualitative way. So it's not a numerical discussion of the analytics of it. But I think it's interesting to go through them. They are 12 steps. So this is something that it's quite extended. But as I said, I think it is interesting to discuss them one by one. The first one is trivial, estimation of wave statistics, and we are particularly interested in the mechanics of waves that is originating the along-shore sediment transport potential at the selected locations. And if you don't have an extended set of data, as I said, you may refer by looking at similar places, similar contexts. In any case, what I suggest, what the literature suggests, is to carefully assess with an expert eye the current shape of the beach. Like when I showed to you the figures of beach erosion, I think you should train your eye to recognize what kind of dynamics originated such erosion. Let's look at more figures with the hope that I can give you some examples. So let's look beach erosion. First of all, when you look for figures over the web, it's usually when I want to get a broad picture, I look just on Google beach erosion like I did here, and I look at images, okay? In these figures, most of them, you cannot use them for your thesis, for publications. I cannot use them on my website. So this is the inconvenient. But from an educational point of view, it's convenient to give to first look at Google in general. Okay, and if you want to find figures that you can use, what I suggest to you is to look at Wikimedia Commons. There are several places where you can get public domain picture, but Wikimedia Commons is the safest. This is something that you can absolutely use. And here I can look for coastal erosion, and you find some pictures, and you also find those that I used in the PowerPoint, like this one. And if you want to get the picture, you click on it like I did here, and you get it here on the right. Click on the link, and then you find the download page. When you click on download, you have several resolutions and the attribution. It's always safe that you put the attribution in the caption, or you give the attribution in the way you deem more appropriate. And you can also modify these pictures. You can also modify them, but in most of the cases, you need to provide the attribution. If you click on full resolution, usually they are very large files, so I don't use the full resolution usually. While I take care of the attribution. Also, there are informations about reusing, if you look at this, et cetera, et cetera. This is Wikimedia Commons. As I said, there are other places where you can reuse the pictures, but it may be difficult to understand whether you can really use them or not. In most of the cases, if the purpose is non-commercial, you can use the picture by providing the attribution. But I suggest to be very careful. I had a colleague that produced a leaflet for a degree program. So it's something that can be defined as commercial if you want, but it's not really for making money. And this colleague took a picture from the web and distributed the leaflet, and then he got a fine of 3,000 euros, and he had to pay it. The university didn't pay for it. So just be careful, because when you get material from the web, the fine may be large. And of course, you have to be very, very careful when you cut and paste the text, because this may be even a crime. And the plagiarism in Italy is a crime. So you have to be very careful, because we had a case of one student that he really cut and pasted a large part of his thesis, but the result was that he was radiated by the university, and he lost also all the exams. So, I mean, I think that in many cases, we are not aware of the risk. So just try to be careful when you take figures from the web. Okay, but let's go back to our discussion on erosion here. So there are some situations, like, for instance, in this case, you see this one, it's clearly a situation where I think it was a storm causing it. This is not a long-term evolution. You understand that it's not a long-term evolution, because a long-term evolution is originating, in any case, a smooth shape. It's not a shape like this, where you see that a lot of energy was concentrated in spikes. And moreover, there was a biking lane there. And so it's not a long-term evolution. It's an evolution that took place probably during a single event. And therefore, in this case, I wouldn't say that this is caused by a long-shore sediment transport. If you look at this picture, this is a different story. I tend to say that in this case, this is a long-term evolution. And clearly, if you see the very smooth shape of it, it's hard to believe that here it's only an across-shore problem. I think there is an evolution along the direction of the coastline. And then there are, in this case, it's hard to say, but, you know, I don't think this is a long-term evolution, but in any case, it's hard to say in this case. It's not so easy. This case as well, it looks like it's an across-shore component that caused it. And this is, I don't see I don't see evident components in the short time scale. When people talk about climate change, rising sea level, this is usually a long-term component, and therefore probably a long-shore component. Okay, anyway, try to get information by looking around, try to understand what is dominant, what is the dominant process, and look at the forms. So if the forms after erosion are very smooth, you are a little bit more happy, you are a little bit happier than when you see forms that clearly testifies highly energetic environments. So when there is a lot of energy, you have to be more concerned than situations where you see a less energetic environment, and typically an indicator is given by the shapes. This is what is important to look at. And just 1 second, okay, now the blackboard is no more put in evidence. Good, now let's go back to our presentation, which is, where is it? Just 1 second. Let me close this. Okay, here it is. Okay, so step 2. Step 2 is the identification of the extension of the intervention. So how long should I go along the beach, along the coastline? Of course, we have to identify, we have to understand the dynamics of the longshore sediment transport. Is it a process that is very concentrated or is widely distributed? And structures should be placed in correspondence of relevant transport. So if you see evidence of relevant longshore sediment transport, this is where you have to start your intervention. And the structure should also end where the gradient in sediment transport is low, because if you have big gradients in sediment transport, it means that you have erosions there. And if you don't have big gradients, it may be the right place where you could hand your intervention. Keep into account that the intervention, the extremes of the interventions are hotspots, are delicate places, because while the intervention, each downdrift protection is protecting the updrift ones, at the extremes, you have a spike, you have a singularity in the shape of the coastline. So this is why at the extremes, you may decide, for instance, to progressively reduce the length of the groins. Instead of causing a sharp interruption, you start to decrease the length and you converge smoothly towards the original configuration. How long is typically an intervention? Of course, it depends on the length of the beach, but it is unlikely that an intervention is made up by more than 15, 20 drawings. So if you consider the distance, which may be in extreme cases 100 meters, I would say, okay, 1 kilometer is fine. Usually we don't see, especially along the coastlines, we don't see much longer interventions. Along the rivers, it may happen that you put a lot of groins even for kilometers, tens of kilometers. Step 3, identification of the design location of the post-project berm. You have a berm in the current situation, you are not happy with it. So how much you want to extend it? Keeping into account that the time required to reach stability depends on, of course, on the extension of your intervention and also the advance of the berm that you wish. Ideally, you want, this is not a difficult step. You have a problem because the beach is becoming too short, and usually what we want is to reestablish a previous situation. And usually the problem is, this is not a big problem. Step 4 is the estimation of the post-project slope of the beach, because the post-project beach is expected to be slightly gentler in terms of slope with respect to the pre-project beach. Clearly, if you extend the beach seaward, what you usually expect is a more gentle slope. In situation where you have to recover an original equilibrium situation, after the erosion, when transitioning from the original equilibrium situation to the current situation after erosion, the result is that the slope of the beach is increased. And therefore, we have to identify what is the slope of the beach that we want to reach after the intervention. Clearly, this is not a big issue as well, because usually we have information on the previous configuration of the beach. Usually we want to restore something that was originally there. And therefore we refer to the original information in order to understand what could be the new slope. And then, depending on the new slope, why the new slope is important? Because we also have to understand at this stage W. We have to estimate W, which is the distance between the low water and high water shore lines. And we should also predict the horizontal distance S, which was indicated in the figure, between the low water shoreline and the berm. So, of course, once we estimated the new berm, the position of the new berm, we have to estimate this horizontal distance S. And also it's important, based on the tide information, to understand the W. And let me just look at the figure, because S, I don't know, less is the distance between the low water shoreline and the pre-project berm. Sorry, it was wrong. Okay, and we are at step 5. Now I propose to stop. Let's take a 15 minutes break as usual. Do you have any question? I take this opportunity, Giorgio, you got my email that I'm teaching next Wednesday and not teaching.
Yes.
Okay, good.
Yes, yes, I saw it. Okay.
Very good. Okay, if you don't have any question now, we take the break.
Okay. See you 15 minutes.
Yeah, 15 minutes. Thank you.
Thank you.
Okay, just 1 second, I check if the recording is in progress. Okay, good. So we are at step 5, as we said, we already discussed it. Now, step 6, identification of the number of bit cells, N, and average gap width, G. This is consequential because we already identified the length of the intervention. So if we identify the number of bit cells, then of course, by dividing the overall length by the number of cells, we get the average gap width. And also we have to identify the groin head width, H. So, of course, for T-shaped groins, we expect that the head is larger than the body of the groin. The width of the body of the groin is indicated here with Z. And I specify symbols because now we make a very simple computation of what we may expect for the resulting gap G. The total short front length of the intervention L, we call it L, which is composed by N cells, is then given by the expression that you can see here. So if I multiply the number N of cells by the sum of G plus H, where H is the width of the head of the groin, of the T shape, I obtain the total length N. This is very simple. And here we assume that all the groins have are T-shaped, have the same shape, and therefore we don't have here the consideration of Z, of the width of the body. Now, we have to design the length and the head width of groins. So the length of the groin, long or short, whatever, and then we have to design H. Okay. How to design these quantities? Clearly, we have to decide whether or not we want a T-shaped groin. And if we see that it's a highly energetic environment, we want to get the max result from the intervention, then we enlarge the width of the head of the groin. And then with the lambda rule, we can predict the resulting shape of the shoreline. We have to take into account that, of course, the larger the H and the smaller the open window between groins. So it's a kind of compromise between, of course, the hope that the intervention is effective and the impact of the intervention itself. Now, depending on the position of the low water shoreline, step 7, we are still in step 7. Length and shape of the groin, as well as the H value, the width of the head, can be determined by making a computation which is based on the application of the lambda rule. So once that we determined the quantity S, position of the low water shoreline, we can use the lambda rule to determine the combination between the gap, which of course conditions S, and the width of the head of the groin, which again conditions S. This is a very simple computation, but let's look at it because it's simple, but at the same time it is easy to make mistakes, especially in the simple calculation. Of course, if we want to bring the, by definition for the lambda rule, if we want to bring the low water shoreline up to the end of the groin, we need a T-shaped groin. And if you look at the figure here, look at the right groin. If you want to bring the blue line close to the end of the groin, you have to make lambda g equal lambda g equal to what? Lambda g should be equal to half of the width of the groin plus half of z. So if you basically impose this condition, you obtain the relationship that you see at the bottom of the slide. So h should be equal to 2 lambda g plus z. So basically, it's if you put it in a different way, if you bring z on the left-hand side, you obtain h minus z divided by 2 is equal to lambda g, which is indeed what we are imposing here. H is the total length of the total length of the head of the groin. If you subtract z and divide by 2, you obtain the length of the semi-head measured from the body of the groin to the extreme of the T. And this must be equal to lambda g, because if you see here the figure how lambda g is measured, so this is the condition that we want to impose if we want to bring the low water shoreline up to the end of the groin. Of course, this is an extreme case which we take as reference. Another possibility could be if we that we take a longer groin by avoiding the T. So if we have the room for going far into the sea, we could take just a rectilinear groin. We can avoid the T, which is in a way disturbing in any case, because for the visual, for many reasons. And we just take a longer groin if it's possible. It may not be possible because if you have the sea level that is the sea bottom that is very gentle in terms of slope, you can go far with the groin. But if the slope of the sea bottom is significant, you can't go far into the sea, and therefore the groin need to be shorter, and then you may use the T in order to maximize the effect. But in any case, it's important to notice that the condition that you see on the bottom of the slide reflects this assumption. We want the low water shoreline after the intervention to be brought up to the end of the groin. Good. Now let's make some development on this condition. In some cases, it may be required that the mean high water shoreline reaches the head. So we have to add W to the quantity lambda g. So if we rewrite the previous expression by writing, instead of lambda g, writing lambda g plus W, we obtain this condition, precisely this condition. So let's say that in general, we may want something in between of it. So we may substitute W with a general quantity X, where X is between 0 and W. And this is an extension of our computation to the case where our reference is the high water shoreline instead the low water shoreline. But there is no complication. The concept remains the same. So what we obtain now, if we rewrite the condition, is that L is given by N, which multiplies H, let's go back here. It's, we use this relationship, L equal N, which multiplies G plus H. But for H 2 lambda G plus X plus Z, and therefore we obtain L equal N, which multiplies G plus H, G plus 2 lambda G plus 2X plus Z. And then if you multiply N by any of the members between parentheses, you obtain the second line. And then by rearranging, by bringing on the left-hand side the elements which contain the term G and putting on the right-hand side the other addendums, we obtain that G is given by, look at the last line, L divided by N minus 2X minus Z. Everything is divided by 2 lambda plus 1. So here, basically, it's the condition. But there are several variables that are still unknown, which are L, let's suppose that is known, the number of beach cells is something that we may have some flexibility. X, we may have some flexibility. And also, let's say, also for Z, we may have some flexibility. It is the width of the body of the groin. But as you will see, there are some indications for it. And lambda. Lambda, we can take 1/3, or we may take something close to 2/3 if we are in an energetic environment. For Z, we have suggestions. X is something that we have to decide basing on our needs, and also N. Of course, we want to minimize N, because if you minimize N, you minimize the number of groins, and you have several advantages, including the cost of the intervention, which is lower. On the other hand, we may need to increase N in order, because if we take an high value of X, we have to decrease. We have to increase the number of pockets, the number of beaches. Okay, and we are still in step 7. If the gap width reduces too much, so if G becomes too small, then we can use the rectilinear groin, as I said, and with its length increased. Okay, that's fine. So in practice, we select a number of cells, N, for identified value of lambda, and a desired value of X, in order to develop a physically reasonable gap width to G. G values less than 20 meters are not generally recommended, as I said, at least for recreational beaches. For obvious reasons, if you leave only small openings, then it's not nice. And keep into account, this is an important thing to say. In energetic environments, the groins may originate rip currents. What are rip currents? Are currents in across shore direction. And these rip currents may be dangerous for swimmers. Let me expand on that. And on the other hand, gap width greater than about 100 meters are not recommended as well, because distance structures may be not effective. For recreational beaches, it is also advisable that the head width are smaller than the gap width, so H lower than G. Yes, you understand why, because if H is comparable to G, you have basically the extension of the gap of the open sea that is lower than the confined part of the sea. So it's not really nice. It looks like a sequence of pools. Rip currents. Let me look over the web if I find something interesting. Rip currents, because they are often encountered into the oceans. So a rip current, often simply called a rip, is a specific kind of water current that can occur near beaches with breaking waves. A rip is a strong, localized, and narrow current of water which moves directly away from the shore, cutting through the lines of breaking waves like a river running out to sea. The current in a rip is strongest and fastest next to the surface of water. Rip currents can be hazardous to people in the water. Swimmers who are caught in a rip current and who do not understand what's happening, or who may not have the necessary water skills, may panic, or they may exhaust themselves by trying to swim directly against the flow of water instead of swimming in the transversal direction. Because of these factors, rip currents are the leading cause of rescues by lifeguards at beaches. And in the United States, they are the cause of an average of 46 deaths by drowning per year. And this is the figure. Don't fight the current, swim out of the current, then to shore. If you can't escape, float, or tread water. If you need any help, call or wave for assistance. So if you put several groins with a small spacing between them, you may originate a rip current for obvious reasons. If you think of several groins, it's like a sequence of channels that can be fueled by waves in the cross-shore direction, and then you have the water, the incoming water brought by waves that flows back to the ocean and may generate a rip current. Okay, step 8, we have now to position the gaps and the heads along a line that is S plus lambda G seaward of the target design berm location, where S is the distance from the new low water profile and the current berm. Step 9, we orientation of the gaps to make them more closely parallel the control line with the average of principal crest orientation. We already discussed this. The aim is to minimize the wave crest angle with the orientation of gaps. If the terminal structure in a field employs a head or spur on its downdrift side, it's better to offset it seaward than landward. This in order to give a contribution to keep the control line parallel to the wave crest. Actually, the solution may be counterintuitive because one may think that a landward offset of the T of the head of the groin would offer a more natural transition from the structure to the beach, like a connection between the structure and the beach. But actually, the lambda rule suggests that it's better to keep the lambda rule and the overall reasoning that we made suggests that it's better to keep the control line parallel to the wave crest. Okay, step 10. Now we have to think of extreme waves and extreme waves that may also come from the across shore direction. And then the aim is to understand what could be the occasional forcing the structures are exposed to, because these structures during storms are subjected to wave forcing, and in some cases they may get damaged or they may ruin under the action of waves. And also it is important to consider what may happen if the longshore sediment transport is caused by unusual waves that deviates a lot from the average wave direction. Adjustment may be necessary, and of course, for this reason, as I said, if we can keep some flexibility in the design, this is why In some cases, we use permeable groins, we use woody groins, because if you take permeable structure are lighter structures, they are structures that can be more easily modified in their orientation. So this is why sometimes they are preferred. And then let's talk about the landward extension of groins. Usually they are put in the landward direction. They are extended up to reach the current, the dune if it exists, or the current berm. Of course, you have to avoid the situation which is really damaging, originating a negative effect, that the groin is bypassed landward. It may happen, because if it's not extended enough landward, if it's not buried into the current berm, it can be bypassed landward, which means that they become like highland and the erosion is probably increased, even with respect to the current situation. And so usually it's buried within the beach fill. And the final step, the elevation of the heads should be determined to minimize wave overtopping during the design event of interest, which typically includes typical seas or high tides. It's not a big problem if during a storm it's overpassed. The important thing is that at the working condition, the groin is not overtopped. Because, of course, unless it is a desired effect, if it is overtopped, you have some bypassing of the sediment transport, and therefore you have performances that differ from what you are expecting. So the elevation of this the stems are the landward end of the groin. It's also called stem, maybe lower than the heads, and like the stem of the tree. And the elevation of the stem may be lower than the heads, but of sufficient elevation to prevent tidal overtopping at high tides. It may be convenient to lower as much as possible the elevation of the stems, because for people walking along the beach, bypassing the groins, it may be complicated. And if you tried sometimes you really need, if they are made by boulders, you really need to climb over the boulders to bypass the groin. And the profile elevation of the terminal structure should be higher than the design beach profile, of course, and which is to be predicted in the vicinity of the structure. And in case of a rock structure, the crest elevation should be not less than 1/2 arm or stone diameter above the predicted design profile, plus some contingency. So you predict the profile, the high water profile, and the low water profile. You take the high water profile, and it's important that the crest is at least 1/2 stone diameter above it. Okay, now let's look at the typical dimensions. Let's give some order of magnitude. Here you can see a cross section of a groin, which is not permeable. And it may be done by boulders, but in this case, it's important to identify the main component of the structure. This is not something that is compulsory. It's not a rule. It's just a suggestion that if we use boulders that are placed over loosey material, we need to take care that the whole structure is strong enough. Otherwise, it is an environment which is subjected to erosion. And if you just put boulders over the sand, the effect of erosion may displace the boulders. it's important that we realize a foundation, and the foundation should be strong enough to distribute the weight of the boulders uniformly, because the boulders don't have a regular shape. So if you create big gradient of pressure, you understand that the water infiltrating into the body of the groin can circulate, can remove the sand where it's can be freely reached, and then the structure is soon damaged. Usually we adopt a core. The core is the central part of the body of the groin, which is composed by material of fine size, with the purpose of creating a structure that is less permeable, that is more homogeneous, and therefore allows to distribute again the pressure over the foundation in a uniform way. The core, the size of the sediments that are used to build the core, can be fine because the core is not directly exposed to the action of water, because otherwise, the energy of water would remove the grain with lower size. And then over the core, we put the armor stone. The armor stone has the purpose of offering a valid barrier against the action of waves. On the other hand, they have some permeability, and their distribution, their weight is distributed over the body of the core in an uneven way, which is fine if for the core, wouldn't be fine for the loose material at the foundation. The core may also be, if needed, may also be very cohesive with the addition, for instance, of some cement, or so the cohesion of the core can be increased with respect to the natural cohesion of the sediments, in order to make sure that there is a kind of solid aggregation that is created. And now let's look at the symbols that we use. With respect to the mean sea level, we indicate with RC the elevation of the crest of the groin, and with lowercase h, the difference between the mean sea level and the beach level, or the sea level, let's say the sea bottom level. We indicate with capital B the width of the crest, and we also indicate with the symbol, I think it is the slope, I think it is an eta P, but let's see. But an important parameter is the slope, the lateral slope of the groin, the slope of the sides of the groin. Now, let's give some orders of magnitude. So, H, which is defined as the depth of the basement of the groin head. This is important because I couldn't remember before this slide where it was measured, because of course it's varying. With respect to the mean sea level, it's from 2.5 to 4 meters. This is the order of magnitude. RC, it's about from 0.5 to 1.5 meters. The depth of the groin basement landward with respect to mean sea level is from 1 to 2 meters. So you see that it's lower, of course, landward with respect to the sea front. RC, I already discussed it. B, width of the groin top from 3 to 6 meters. Very often we have sidewalks on the top of the groins, which allow people to walk over them. And 1 over NP, the slope of the groin side, this is an important parameter, from 1.11 to 1/2. 1.1 is rarely used, but we will dedicate some time to the analysis of armor stability in the groin bodies. And then there is the thickness of the foundation from 0.5 to 1 meter. In the foundation, usually we put some material to strengthen the foundation of the groin. It may be a geotextile. It may be used also concrete, but it is preferred the geotextile because it's a flexible layer. While if we use concrete in this environment that is rapidly subjected to erosion, may not be a good idea, but in some cases it can be used, it has been used. These are the typical dimensions, and then let's conclude this discussion with a few words on a more quantitative design of what happens, because let me go back in just one slide. The discussion so far has been concentrated on empirical rules of thumb, has been concentrated on orders of magnitude and qualitative description of the design. But of course, it's still open the big question, how to get some more quantitative estimation. This is not always needed. Remember that when you project structures, you are not always obliged to make a refined analysis, a refined computation at fine spatial scale, fine time scale of what's going to happen. Because for simple structures, this is not required. When the structure becomes more complicated, typically, you need to get the approval of the project from a responsible authority, which may be, for instance, a port authority. So you have, depending on the size of the structure, the policies for design and the rules for design, depending again on the size of the structure, may suggest that you get the approval from a responsible authority. This happens in any branch of engineering. So if you think of dams, for instance, there is a rule which says that if the dam over a river is higher than 15 meters, you have to get the approval of the dam from the national authority of dams. And if it is lower than 15 meters, you don't have to get this approval, but the only required approval is by the regional administration. The regional administration typically doesn't ask for a refined assessment numerical model or a small scale model, which means a reproduction in the lab of the intervention, which, by the way, it's often done with coastal defenses and also with harbor interventions. What the authority may recommend is, I want to see in the lab a small-scale model of the coastline with and without the presence of your proposed intervention, and then you run a wave generator into the pool in the lab, and you get a simulation of what's going to happen. But this is required only for big solutions, only for complex, very complex structures. And so it depends. In most of the cases, for very small interventions, you may allow to move forward only with the application of the lambda rule. So you make your empirical estimation, you get the approval from the administration, and especially if they don't see any risk related to it, maybe not even a financial risk because the structure is flexible, is a temporary structure, they may allow it. Instead, in some cases, you may require of making additional analysis on a laboratory experiment, or another solution that is frequently applied today is the numerical model. So what is the difference between these two solutions? First of all, let me check if I have a link in my webpage on some videos of laboratory experiment. These are very interesting. I don't think I have a video here. Let me think of, let me see. I think I have a link in some other lectures. Let's see here. No. Okay, so I think there is a lab for a lab that performs a lot of lab experiments on coastal protections, which is the Deft Hydraulics Lab. And let's see if they have very nice videos. And let me see through spinning bases. This one is not sure. It's let me see this one. And because as soon as we get on YouTube, I think this is not very technical. I wanted to get a video because there are some videos. Let's see, big wave. Some videos that are nice. The delta show. Okay, I think they have a big flume which simulates big waves, and let's see. I think here. I visited once, and it is amazing what they do here. Let's see. There is no audio, so don't worry. Don't worry, Giorgio, if you don't listen any audio, it's not necessary. Let's just wait for.
Okay.
Wait for the end of the advertisement. Okay, this is the big wave that they generate with a wave generator, and you see the size of the wave compared with the size of the persons. They bring the wave to breaking, and then on the other side, it's I think it is reflected. I'm not sure if it is reflected back or let's see this other one. And here there is nothing related to coastal erosion, but it is this is the largest facility in the world for wave generation. It is a flume, and they use it in order to make several tests. I don't see any coastal protection here, but you could also make a test on coastal protections. But you get the idea that these lab experiments are indeed intensive, and they need a lot of resources. And the fact that this is a large facility is important, because when you make a small scale model, you can't reduce the scale too much. Because you understand that if this flume was incredibly small, very tiny, now I think we can keep going with the other videos. If they were very tiny, then it would be a problem, because you can't recreate turbulence, because viscosity dominates. And there are important scale effects. I think here they are testing a kind of protection of geotextile or something like that. So you cannot reduce much because of the scale effects. and therefore you require large facilities. So the moral of the story is that these tests cost a lot of money, and therefore people today tend to prefer the numerical models. Numerical models, they can simulate the effect of turbulence, it's no problem, and they need a lot of computational capacity, but this is not a problem. The problem of the numerical models is their numerical error, which implies, and also the reliability of the theory, because you have to describe with partial differential equation these processes. So while in the lab, you don't need to describe the theory. You make the experiment, you make sure that everything is, the scale effects are small enough. So the lab doesn't require a theoretical interpretation, which is by definition uncertain. So the lab at the end of the story is considered a more reliable test, but it's more costly. So depending on the requirement of the responsible body, you may be required to perform a lab experiment, or a numerical model may be just enough. And in some cases, they don't really understand the difference. So it is a bit problematic. And of course, people say the best thing is to integrate. You make a numerical model of the lab experiment, and if you see that they match, it means that the numerical model is reliable, and also the scale effects are limited. On the other hand, you understand that it's not possible to, especially with limited resources for limited, for designs of limited complexity, it's not possible to have everything available at hand. Okay, so now let's get some more details on numerical models. What you see here, it is something that if you attended my lecture on coastal engineering, you have already seen. It's a representation of the one-line model, numerical model, which of the beach remains constant. It doesn't change after erosion. So basically what happens after, in this case, after accretion, is that you have the formation of the yellow wedge, which was not there before accretion. So you have an advance after accretion of the beach line, of the coastline of delta epsilon. And this advance is such that the slope of the beach is preserved and the direction of the coastline is preserved, which is, of course, not true. We already know that when you have accretion, there is a change in the slope of the beach, and you may also have a change in the direction of the coastline. On the other hand, within small spatial steps, we can assume that this assumption holds. And therefore, what we need to do is to apply this model to study the accretion of the beach on very small time steps, delta y, you see here. And so basically, we split our beach in several delta y's. We compute the flow of sediments in, Q in, and the flow of sediment out, Q out, by assuming that you have a certain strength in terms of erosion of the waves. And so if the strength of the wave increases, you have that Q in is lower than Q out, because during the delta y, the strength, the energy of the waves increased. And therefore, it means that if you have more outflow of sediments than inflow, it means that you have erosion. The opposite is true when the Q in is higher than Q out. Therefore, you split the beach in several pieces. You apply a sediment transport formula, and we consider the CRC formula, if you remember. We are not interested here. We already did it in the fall semester, or you will do it in the next semester, maybe. And but by these assumptions, delta y by delta y, we can estimate how much the beach moves back and forth. And Of course, you will have zones where you have accretion, zones where you have erosion, you have a displacement of beach, which is simulated by the numerical model, with the very relevant assumptions that the shape of the beach doesn't change. But the principle is simple, I mean, in itself. Of course, the computation is subjected to uncertainty and numerical approximation. So if you did the exercise with me, or you will do it, you will see that the final shape of the coastline, if you increase delta y or you increase the time step of computation, becomes unreliable, because also the time step is important in a numerical model, not only the spatial step, because what you compute with the numerical modeling is an average over time and over space. So there are several models applying this principle of different complexity, because we made, or we will make a simple exercise where it was clear that we need to simplify the computation if we want to make it short. And if we want to be able to make it under R, for instance, we can write a very simple code by making several approximations. There are models which apply the same principle but do less approximations. And one model that is largely used is called, it's not mentioned here, but in the next slide, it's called Genesis. Genesis, I'm not sure, I don't think it's public domain. I'm not really sure, but I don't think so. I never tried to download it. It's widely used, and the good thing with using a model that is pre-prepared, probably it's a commercial one, is that it's already tested, and they make a lot of checks at each time step, at each spatial step, to make sure that the result is coherent with a principle of homogeneity and veridicity of the estimated changes. The bad thing of using a model that is pre-prepared is that you may have a limited capability to understand what the model does, because these models, in doing these checks, repeated checks, they, at the end of the story, lack of transparency. If you write your own code, you have the perfect control on what you're doing. You may make mistakes, but on the other hand, with the full awareness of what you're doing, you have also the opportunity to detect these mistakes. If you use a commercial software, sometimes we don't look at the warnings. Usually these softwares issue warnings, but they are many. So we don't have time very often to look at all of these warnings, or we may be lazy. And even if we look at the warnings, we don't understand to what extent these warnings may be effective on the results. So there are pros and cons, but for sure the use of software is recommendable. On the other hand, my advice for you is try to understand as much as possible what the software is doing. If you get a mistake, you cannot say to the court, in front of the court, that it was the software the problem. I mean, at the end of the story, we are engineers, we bring the responsibility, we bear the responsibility of what we do. So for this reason, my suggestion is, okay, fine, using the software, I use them. On the other hand, try to understand what they do. If you understand what a software does, you can also get a kind of sensitivity to mistakes. You gain an ability to look at the results and to detect if there is something that may be wrong. So I think we already discussed this, some assumption of Genesis. Let's see. One assumption of Genesis is still that the beach profile is unchanged. Okay, so it can move back and forth. We already discussed it. It's the one-line assumption. It's called one-line assumption. It's adopted by Genesis. And okay, I think another important assumption is that sand actively moves over the profile to a certain limiting depth, beyond which the bottom does not move. So when you move the sand seaward, there is a limit in it, which is confirmed by our experience. Usually the sand doesn't reach the very deep sea bottom. When it moves along shore and remains confined in a belt that is between the coastline and a limiting depth of ocean, which is called the depth of closure. It is estimated in Genesis the depth of closure has twice H max, where H max is the maximum annual wave height. So this is important to notice. It's also an important indication of the order of magnitude. So to what extent sand can be transported into the ocean? Up to a max depth, which is about twice the maximum annual wave height. When we say the maximum, you may ask for what return period. And when there is no specification of the return period, like in this case, you can take a mean of the annual maximum wave height. But when there is no specification in the Italian context, it may mean either the mean or the value corresponding to 100-year return period. I don't know for what reason, but in Italy, if you talk about an extreme something related to environment, extreme wave, extreme flood, the implicit assumption is that extreme means 100-year return period. This is related to several rules suggesting as design variables the extreme in engineering for 100 years. And this is the implicit assumption when one says extreme wave height. And in this case, it's not extreme, it's maximum annual wave height, which is actually a random variable. Every year you have a maximum, and with no specification, and in this case, I know that it's around the mean. You take the mean of the max annual. Now, it's a model based on mass conservation. We don't go into the details because there is another lecture in coastal engineering going into the details. And now, what is important is to discuss permeability. It's time to discuss permeability. So in Genesis, there is a simple approach that is used to deal with permeability, which I think is interesting because it's another empirical suggestion which I think is appropriate. So the fraction F of sand that is transported over a groin, so downdrift a groin, not over meaning above, but over meaning downdrift, and through because we allow for permeability, it is represented by a permeability factor P. And the amount passing around the seaward end is, okay, so over a groin probably it includes, but I don't think it is a correct way of saying that, even if I wrote it. I think that, let's say, the fraction of sand that is transported through a groin is represented by a permeability factor, and the amount passing around the seaward end is represented by a bypassing factor. So I don't think over means overpassing here, because permeability is not related to overpassing. So we can estimate this fraction with a very simple relationship that you see there, where permeability is between 0 and 1 with obvious meaning. 0 is impermeable, 1 is full permeability. And also the bypassing factor is comprised between B 0 and 1. B is comprised between 0 and 1, where 0 is no bypassing and 1 is full bypassing over the groin. So you multiply the permeability by 1 minus B, because of course you have to subtract the fraction that is bypassed, and then you sum this product of permeability times 1 minus B to the bypassing, and this is the fraction. And the permeability can be simply estimated as a ratio between the area of the windows and the full area of the body of the groin. So area of the void plus area of the void and the structure and the hard structure. So here it's noticed that for typical groin shapes, because it may be not so easy to estimate permeability as I previously suggested, for typical groin shapes, there are suggested p-values. Groins made by boulders have a p-value that is close to 0, as I anticipated at the beginning today. The actual volumetric sediment transport rate at groin is related to the potential rate with the simple formula. We multiply the fraction of sediment transported behind the groin by the potential sediment transport, and then we obtain an estimate of what is actually bypassed. Okay. Here there is some more on the permeability factor, which can be assigned based on groin elevation, grain porosity. Here, actually, they take into account elevation, yes. So I think it makes sense that they consider the overpassing with the impermeability. I didn't, sorry if I didn't recollect this. So I think it makes sense. Okay, so the permeability factor may be estimated again based on groin elevation, groin porosity. Porosity is actually the ratio between the void and the full body of the structure, and the tide range. And the bypassing factor can be then computed with this relationship where dg is the sea depth at the groin seaward and at a particular time step, of course, because it may be, and DLT is the depth of active longshore sediment transport, which can be assumed to be about 1.6 times the significant breaking wave height. And therefore, groin bypassing is dictated by the sea depth at the groin seaward end and wave behaviors. Okay. There are empirical formulations, as I said, assumptions used within Genesis to estimate bypassing for angled groins, shape of the sea bottom profile, impact of refraction and diffraction, and we are not interested in the details. In general, I'm not asking anything at the exam related to Genesis, and I may ask how permeability is fraction of bypassing is estimated. And I never asked this one. Anyway, it's in the concept that in poor words, I want to tell you that what we are discussing is relevant, but not for the exam. So there are other empirical formulation, and then that's it. Let me make a conclusion of this discussion on design of groins, which is actually not really finished because, one second, because we will talk in the next lecture, next Wednesday, we will talk of stability of rock and concrete armor units, which is related to groins. But for what is related to the design of the body of drawings, we are done. And I just want to make a final consideration. So, I mean, the stabilization of beach field, of beaches by structures, it is much complicated in sites where the erosion stress is severe. And so maybe that, I mean, what I want to say is maybe that breakwaters and groins are not enough. And in some cases, as I said last Wednesday, you may need to couple these interventions with other actions like beach nourishment or beach scrapping. I'm not sure if I mentioned it to you, which means that during the extreme conditions, during the winter, you take the sand back into the beach in order to avoid that it's eroded. And so it's you may have to consider the integration of several solutions. And I want to stress once again that it is extremely important that you try to elaborate a perception of what's going on, of what was the mechanism that brought the beach from a previous condition to a current condition, or if you want to establish a condition that was not previously there, you have to be even more careful. So what is important is to gain, as I said, a perception of the local context and an expectation of how these many mechanisms may evolve according to a new situation. And when possible, you have to get all the available information, and when possible, if you can keep some flexibility. And sometimes it is really possible, but we don't realize that it is an opportunity. And we, in fact, if we don't realize it, we lose an opportunity. So besides using sophisticated design procedures, it is as usual very important that, and this is the difference between a pure engineer and a pure scientist, you try to understand from a technical point of view how your solution is to be designed and adapted. Okay. Now, we still have, I would like to take these 10 minutes to, first of all, I want to make sure that you don't have any questions so far. Okay, let's use these 10 minutes to make, if you agree, an introduction of the stability of rock and concrete armor units. I know that you did something with Professor Archetti. First of all, let me see. No, I don't have PowerPoint here, but I will prepare it by next Wednesday. So I know that you talked, I think you talked already with Professor Archetti. You had some lectures on design of breakwaters, I think, yeah. And I think that probably she already talked about empirical formulas for checking the Hudson formula, maybe for checking the stability of rock and concrete armor units. I want to expand a little bit on what she did. I am pretty sure that I'm not overlapping much. I made a check with her. Maybe that I need to remake it because during the pandemic something changed. But it is an issue that is, I think, interesting, that comes forward when designing several coastal structures, like not only breakwater and groins, but also beach protections, like revetments and protections made with boulders and with artificial material like the tripods that you see in this picture here. By the way, you see in this picture that was taken by Wikimedia Commons that I put the attribution in white on the picture for the reasons that I mentioned to you before. So this is extremely relevant. I think it's also interesting. What I would like to make is to expand over what Professor Archetti is teaching by including a more physically based analysis of the equilibrium of these units by referring to a very simplified situation. And let me anticipate already now that there are several shapes of, just 1 second, I think it's here somewhere, a link to a figure, several kind of shapes that can be used besides boulders to make, to realize armor units. Let me check. Yeah. I think I have a link, but it's not ready, so, okay. Of course, I also found several pictures of tripods, but okay. Tetrapod, okay. They are called the tetrapods. I think there is also, let's see, because there are several shapes that can be used. This is what I wanted to convey. Tetrapods are frequently used because they are not really looking like natural shapes, but when combined with natural shapes, they don't look so bad. And in this case, they are poorly combined. And in this case, even in this case, they are not really very good looking. But there is an advantage because the advantage is that this can be produced artificially, while boulders can be, if you cannot find the boulders close in the vicinity, it's a problem because you have to bring them. If you have to bring them at a huge distance, you understand it's a bit of a problem. So where boulders are available, we use them, but where are not available, we use these artificial structures, which it's very interesting to look at the shapes that they may have. And there are several shapes that are produced, and some of them look even more artificial than those ones. And let me see if I get some figure of because some of them are shaped in a way that they lock each other. The tetrapod can't lock each other, and they are T-shaped. Some of them have shapes that are conceived in order to lock each other. Let me see if I have tetrapod. By searching for tetrapod, I think it's a little bit better. And let me see, for instance, you see those ones here, or those ones here, you see that probably these ones are fixed with a cable or with some anchorages. You see these ones, these are, you see the shape, it's really, this is a video showing the several different shapes. These ones, these are combined. These are, I mean, here it's clear the intention of realizing something that is good looking. Anyway, you see how many solutions the industry is proposing. Okay, this is a presentation. We already went through it. So their stability, analyzing their stability is indeed interesting because also the stability depends on the shape of these units. We will refer to a very simplified case which can be schematized by a cube, boulder with the dimension of a cube that is placed over a slope. And then we will analyze the equilibrium of the forces which are caused by the hydrodynamic force. It is the force in blue that is trying to bring this is a component of weight, of self-weight, that tends to bring the boulder towards the base of the structure. And then there is an hydrodynamic component, which is directed in the upstream direction, but it also causes a backflow, which is in a way contributing to destabilizing the unit. And then we have the friction between the boulder and the slope. And so we will make an equilibrium, and you will see that we find a simple relationship that helps us to assess the limiting condition for stability, what we call critical equilibrium. But I think I don't want to anticipate anything, and I just want to say that this approach will be then compared with the more empirical approach, which is given, for instance, by the Hudson formula. But I think it's interesting that you get a full overview over this problem, because when it comes to practical design, this is called the Shields approach. The Shields approach is, in some cases, recommended. Okay, I think we can stop here. Do you have any question? Okay, very good. Grazie Giorgio. Thank you very much. I see that you got the message from Professor Archetti for tomorrow. So enjoy your guest. I don't know who is. I'll ask Renata because I'm curious. Thank you very much, and see you next Wednesday then.